Assalamu alaikum. So today we'll discuss the steady state analysis of synchronous machine, and for that I will recall some concept from the balanced steady state Phasor relation. So here I will start with the balanced steady state Phasor relation. Now for balanced steady state condition, we know that omega E is constant. So here for balanced steady state condition, omega E is constant. So simply any function in ABC reference frame can be written as Fas equal to square root of 2 Fs cosine omega E t plus theta EF of 0. Now Fs here is the RMS value, and theta 0 here is the initial angle. So remember that f can be any function. So here I will write f can be any function. So f can be current, voltage, or flux linkage. Now, if we need to use a phasor to represent this time domain signal, then Fas will equal to the real part of square root of 2 Fs exponential of j theta E f of 0 exponential j omega t. So as a phasor, Fas as a phasor will equal, I will take the RMS value as a magnitude for the phasor, so Fs, and I will take the phase as the angle for the phasor, so this will be exponential of j theta EF of 0. And this is actually the Phasor representation. Now in the same fashion we can write the Phasor representation for the Fbs and the Fcs. So here we can write Fbs as a time domain. This will equal to square root of 2 Fs cosine omega Et plus theta EF of 0 minus 2 pi over 3, and this will equal the real part of square root of 2 Fs exponential of j theta EF of 0 minus 2 pi over 3 exponential of j omega Et. So as a phasor, Fbs as a phasor will equal to Fs exponential of j theta EF of 0 minus 2 pi over 3. The same thing we can do it for the Fcs. So Fcs in time domain equal to square root of 2 Fs cosine omega Et plus theta EF of 0 plus 2 pi over 3, and this actually is the real part of the square root of 2 fs exponential of j theta ef of 0 plus 2 pi over 3 exponential of j omega et. So as a phasor, fcs as a phasor will equal to fs exponential of j theta ef of 0 plus 2 pi over 3. And recall that from the Euler identity we know that exponential of j theta is equal to cosine theta plus j sine theta. That's why we are taking here the real to represent the temporal. And this is also the phasor representation for the FCS, the phasor representation for the FBS, and already we have the phasor representation for the FES. Now, if we do the transformation from ABC to the QD reference frame, so using KS transformation matrix to transform the FABC to a function in the QD0, which means that given FAS, FBS, FCS, using the transformation matrix, we can calculate FQS, FDS, and F0S, of course. And we know the transformation matrix from our previous lectures. So, doing the transformation, yields FQS equal to square root of 2 Fs cosine omega e minus omega multiplied by t plus theta ef of 0 minus theta of 0. Now, this can be written as the real part of square root of 2 Fs exponential of j theta ef of 0 minus theta of 0 exponential of j omega e minus omega t. So as a phasor, FQS as a phasor, this will equal Fs exponential of j theta ef of 0 minus theta of 0. So this is the phasor representation for the function acting along the q-axis. The same thing during the transformation or from the transformation. If we do the math, if we evaluate this transformation, we will get also FDS equal to minus square root of 2 Fs sine omega e minus omega all multiplied by t plus theta ef of 0 minus theta of 0. So simply this can be written as the real part of square root of 2 Fs exponential of j theta EF of 0 minus theta of 0 multiplied by exponential of j omega E minus omega t, and here we need to multiply by j. Why? Because this is the sign. So simply, if I recall the Euler identity, exponential of j theta equal to cosine theta plus j sine theta. So here the real part is a sine, so I need to multiply here by j. So this will be j and this will be j squared. So here j exponential of j theta is equal j, let's write it, minus sine theta plus j cosine theta. So simply here the real part is the minus sign, and here Fds is minus, which means it's acting in the opposite direction of the real dx. So if we compare the form of the Fds as a phasor, which I will write here. So now Fds as a phasor will equal to j Fs exponential of j theta EF of 0 minus theta of 0. Now this actually is the phasor representation for Fqs. So simply from here we can say that Fds as a phasor is equal j Fqs as a phasor. Now if we look into the representation for the Fqs and Fds, we can note that the time domain dependent of the signal, which is in the exponential of j omega E minus omega multiplied by t here and here, this time dependency will vanish if the reference frame is rotating by a speed which equal to the sequence speed, which means that omega equal to omega E. If this is the case, then the exponential here, the exponent of the exponential will be equal to 0. So this term will equal to 1. So simply the phasor representation of the Fqs and Fds in the rotor reference frame or in the sequence rotating reference frame when omega equal to omega E will be constant. Otherwise, if omega not equal to omega E, then Fqs and Fds are sinusoidal quantity. So here I can write a note for you. If omega not equal to omega E, then Fqs and Fds are sinusoidal quantity. While if omega equal to omega E, then the phasor in the Q and the D are constant quantity. And simply this can be understood from the representation here and here. The time dependency is in this term, and this term will equal to 0 if and only if the reference frame is rotating by speed equal to omega e. So simply this exponential j omega e minus omega t will equal to 1 if and only if omega is equal to omega e. And for synchronous machine, actually, omega is equal to omega e. So simply here, for synchronous machine, omega is equal to omega e, which means that Fqs and Fds are constant. Now, another thing is regarding the initial angle of the reference frame. We know theta EF0 is the initial angle of the time domain function, while theta of 0, this one, is the reference frame initial angle. And this one we can attach it anywhere, because simply we can assume the initial angle for the reference frame to be started anywhere in space. So without loss of generality, we can assume that theta of 0 is equal to 0. So we can assume without loss of generality that theta of 0 is equal to 0. Now, if theta 0 is equal to 0, let's write here the Phasor representation for the FAS. So FAS as a phasor is equal to Fs exponential of j theta EF of 0, and Fqs as a phasor equal to Fs exponential of j theta EF of 0 minus theta of 0. Now, under our assumption that the initial angle of the reference frame is 0, so simply from here we can write that Fas as a phasor is equal Fqs as a phasor, under the assumption that theta of 0 is equal to 0. The meaning of theta of 0 equal to 0, simply, if this is our ABC axis, now at the start, at t equal to 0, this will be the QS, and this will be the DS, and now the reference frame is rotating by omega e. So at t equal to 0 here, so at t equal to 0, then theta of 0 is equal to 0. Remember, theta equal to what? Theta is equal to the integration of omega tau plus theta of 0, and this will equal to omega t plus theta of 0. So at t equal to 0, we'll have theta equal to theta of 0, and here I'm attaching the q to the a at t equal to 0. So by assumption it's 0, and this is without loss of generality because we can assign the reference frame anywhere in space. Now, also we need to recall the electromechanical torque of the synchronous machine at this state. So simply, here also I will recall with you the electromechanical torque of synchronous machine. Now TE was equal to 3 over 2 P over 2, and here I'm having three terms for the torque. The first one is the LDS minus LQS IDS IQS, plus the second term was the field torque, which is the LMD IQS IFD dash, and the third term was the damper winding term, which is the LMD IQS IKD dash minus LMQ IDS IKQ dash. Now this is the electromechanical torque of the synchronous machine in the QD reference frame, in arbitral reference frame. Now in rotor rotating reference frame, the steady state operation of the synchronous machine, or at steady state, let's say. So here I will write at steady state, IDS will equal IDS capital. So here I'm using the capital letter to represent a quantity at steady state, and this is constant. Why? Simply because the reference frame now is rotating by a speed which is equal to omega e. So all the phasor in the QD reference frame are constant quantities. The same thing is applicable for the IQS, which be substituted by IQS capital, and this is also constant. The IFD is also constant, IF capital, and we know that omega R now is equal to omega E, and this is also constant. And because the rotor is rotating by synchronous speed, then there is no field will be crossing the damper winding, so there will be no induced voltage across the damper winding. So simply this means that IKD dash will equal IKQ dash will equal to 0. That's why at steady state there is no damper winding torque. So simply keeping those relations on, and we can write the torque expression at this state. So here the torque expression at the steady state. So TE will equal to 3 over 2 P over 2 L MD IF IQS plus LDS minus LQS IDS IQS. Now also we can rewrite the torque in terms of the reactance. We know that X is equal omega L, and here we having L and L. So if I multiply by omega and divide by omega, the torque now can be written in terms of the reactance. So simply TE can be written as 3 over 2 P over 2 1 over omega base, and here I will multiply omega base L MD IF IQS plus omega B L ds minus L QS I ds IQS. So now this actually is the XMD. So this will be the XMD, and those will be the XDS minus the XEQS. So now we can write the torque TE equal to 3 over 2 P over 2 1 over omega base, the frequency that the reactance is calculated in. And if we have a single excitation system, then omega B is equal to omega E. So this will be the XMD IF IQS plus XDS minus XQS IDS IQS. So simply this one, we know it's the field torque, but also we can call it the reaction torque, because it's the reaction between two currents, the field current and let's say the torque component of the current in the synchronous machine, IQS. So simply this one can be called the reaction torque, while we know that this term is the reluctance torque. So simply at this state we have only two terms in the torque, one due to the field or the reaction between the IQS and IF, and the second one is due to the reactance torque. We don't have damper widening, and the reluctance torque is only appear in the salient pole machine when LD not equal to LQ. However, in the cylindrical machine, we know that the reluctance torque is never there. Now, what about the voltage equation at this state? So the first thing here, let's recall the voltage equation in the rotor reference frame. So here I will write recall the voltage equation in rotor reference frame. Now VQS in rotor reference frame was equal to RS IQS plus omega R lambda ds R plus d by dt of lambda QSR, and VDSR equal to RS IDS R minus omega R lambda QSR plus d by dt of lambda DSR. Now the flux linkages, lambda QSR equal to LLS IQSR plus LMQ IQSR plus IKQR dash. Now if I spread the variable, this will equal also LLS plus LMQ all multiplied by IQSR plus LMQ IKQ R dash, and this can be written as LQ IQSR plus LMQ IKQ R dash. The same thing here we can do for the flux linkage acting along the d-axis. So lambda dsr equal to, let's spread the variable, correct the term. This will be the L d I dsr plus L md multiplied by if d dash r plus ik d dash r. Now at this state, we know that at this state all the quantity is constant, so this simply means that d by dt of a constant value will go to 0. So so at this state this term will go to 0, this term will go to 0, and we'll use capital letter to represent all the variables here, and the damper winding current will go to 0. So simply this will go to 0 and this one will go to 0. So from here we can get the voltage equation at this state. So here we will write the voltage equation at steady state. So I will use the capital letter to represent the variable. So FQS will equal to RS IQS plus omega E, and instead of lambda ds I will use LD IDS plus LMD IFD, and there is no damper winding. So this will be the LDS IDS plus LMD IF. Now the same thing here, VDS will equal RS IDS minus omega E, and instead of lambda Q of S we have only this term, which is the LDS IQS. So here this will be the LQS IQS. Now those voltage equation at this state also can be written in terms of reactance. So simply here in terms of reactance, VQ of S will equal to RS IQS plus omega E over omega V X DS I DS plus X MD IF and B ds is equal to rs I ds minus omega e over omega b x q s I q s. Now simply here I will write a note for you that omega e is equal to omega b in single excitation system. So now we have the voltage equation at steady state. Sometimes it's better to represent the phasor in terms of the rotor angle. So here we will rewrite the phasor in terms of the rotor angle. So let's recall that in rotor reference frame, we can write FQ SR equal to square root of 2 Fs cosine theta EF minus theta R. Now, and F DSR equal to minus square root of 2 Fs sine theta EF minus theta R. This is not different representation, this is the same representation, because recall that theta EF is equal omega ET plus theta EF of 0, and theta R is equal to omega RT plus theta R of 0. So simply if I add theta EF here and theta R here, we are getting cosine omega E minus omega R, or multiplied by T plus theta EF of 0 minus theta R of 0, which already we wrote in the start of the lecture. So simply this means that in terms of theta R, we can write the FQS and FDS equal to, this is the real of square root of 2 Fs exponential of j theta EF minus theta R, and this also we can write it as the real of j square root of 2 Fs exponential of j theta EF minus theta R. Now sometimes it's better to write the phasor in terms of the rotor angle. So in terms of the rotor angle delta, where delta equal to theta R minus theta EV. So simply delta is the displacement of the rotor relative to the terminal voltage. So here we can write that delta is the displacement of the rotor relative to the terminal voltage. So if we use the rotor angle instead of theta r, we'll have that theta r will equal to delta plus theta e v. So simply here, if we have Fqs, which equal to square root of 2 Fs cosine omega e minus omega t plus theta ef of 0 minus theta of 0, and we have here Fds, which was equal to minus square root of 2 Fs sine omega e minus omega t plus theta ef of 0 minus theta of 0. Now, in rotor reference frame, omega will equal omega r, and this theta will equal theta r and theta r. So, simply if we separate the variable, we know that theta ef of t will equal omega e t plus theta ef of 0, and theta r of t will equal omega r of t plus theta r of 0. So now we can write Fqsr equal to 2F equal to square root of 2 Fs cosine theta ef minus theta r, and Fdsr equal to square root of 2 Fs in the minus here, and this will be the sine theta ef minus theta r. This to show you that this is not different representation, this is the same representation, but simply in the rotor reference frame. Now, in terms of the rotor angle, we know that theta r will equal delta plus theta ev. So simply, if we substitute, we'll find that Fqsr will equal to square root of 2 Fs cosine theta e f minus theta e v minus delta. And recall that theta ef will equal to omega e t plus theta ef of 0, and theta ev will equal to omega e t plus theta ev of 0. So if I substitute those here, we'll have Fqsr will equal to square root of 2 Fs cosine theta ef of 0 minus theta ev of 0 minus delta. So simply here, Fqsr can be written as the real of square root of 2 Fs exponential of j theta EF of 0 minus theta EV of 0 exponential of minus j delta. The same thing here. We can write F dsr to equal the real of j square root of 2 fs exponential of j theta EF of 0 minus theta EV of 0 multiplied by exponential of minus j delta. So now we can write the phasor in terms of the rotor angle. So also, if the terminal voltage is the reference, if we assume that the terminal voltage is the reference for all the phasors, then Fas as a phasor can be written as Fs exponential of j theta EF of 0 minus theta EV of 0. So here I'm assuming that the terminal voltage is the reference. So simply, if F is V, this means that theta E F is equal to theta EV, and the exponent will be equal to 0, so the exponential is equal to 1, and Fas is equal to Fs. So if this is the case, if we multiply this one by square root of 2, so here we can say square root of 2 Fas exponential of minus j delta, this will equal to square root of 2 Fas cosine theta EF of 0 minus theta EV of 0 minus delta plus j of square root of 2 Fs sine theta EF of 0 minus theta EV of 0 minus delta. So simply this term here is the FQSR, and this term here is the minus FDS, sorry, this FDS, this would be the FDS. So from here we can write the relation between the FAS and FQS and FDS. So square root of 2 FAS as a phasor exponential of minus j delta, this will equal to FQSR minus j FDSR. And remember, this one's phasor, but those are not phasor. Those are not phasors. Those are quantities. So if F, we know that F is any function. It can be voltage, it can be current, it can be flux linkage. So in terms of current, so in terms, or let's say in terms of voltage. This means that square root of 2 VAS as a phasor exponential of minus J delta will equal to VQSR minus J VDSR. Now I will substitute the value of the VQS and VDS here. From where? From here. We have the F, or we have VQS and we have VDS. So if we substitute it, we will get square root of 2 VAS as a phasor exponential of minus J delta equal to RS IQSR plus omega E over omega B X D I D S R plus omega E over omega B X MD IFD dash R minus, this is the VQ minus J. Now I'll put the VD, so this will be RS IDSR minus omega E over omega B XQ IQS. So this actually is the VQS and this is the VDS. So if we spread the variable and we can write VAS as a phasor equal to RS plus J omega E over omega B XQ multiplied by IAS. Here the same. We can write also that J square root of 2 IAS as a phasor exponential of minus J delta will equal to IDSR plus J IQSR, which we already use here. So this is as a phasor plus 1 over square root of 2 multiplied by omega E over omega B XD minus XQ IDSR plus omega E over omega B X MD IFD dash R, all multiplied by exponential of J delta. Now simply this one we know from this relation here. So here if we multiply by J, we can say that this should be J square root of 2 FAS exponential of minus J delta will equal this will be the J FQSR minus J square FDSR. So now this will equal to FDS plus J FQS, and this is the relation that we also use here. Now, if we define this term as EA as a phasor, so now we can define EA as a phasor, the back EMF as a phasor, or the induced voltage as a phasor, equal to 1 over square root of 2 omega E over omega B XD minus XQ I DSR plus omega E over omega B XMD IFD dash exponential of J delta. In this case, we will reach the steady state voltage equation of the synchronous machine, which is VAS as a phasor is equal to RS plus J omega E over omega B XQ IQS plus EA as a phasor. Now, for a single excitation system, we know that omega E is equal to omega B. So we are getting the steady state phasor representation. Here IA as a phasor, which is RS IAS as a phasor plus J XQ IAS as a phasor plus EA as a phasor, and XQ is the synchronous reactance. So simply we are reaching to the well-known voltage equation at steady state for the synchronous machine, which is the VAS is equal to RS IAS plus XS IAS plus EA. So simply this is the VAS, this is the RS, this is the XS, and this is the internal voltage, which is the EA. So it's plus minus, and this will be the IAS. So this is the voltage equation of the synchronous machine at steady state. And the next lecture I will discuss with you a numerical example and how to calculate the synchronous reactance and the stator resistance from the open circuit test and the short circuit test. So simply here, this is the synchronous reactance. So until the next lecture,